Hey everybody, welcome back to another video lecture on Unit 5 and how ionic compounds react in water. And this, just so you know, is going to be a long video. I don't know exactly how long it is because it's the beginning, but I know that when we're dealing with ionic equations and net ionic equations, this can be a tough thing. So we have to take our time and go through this and make sure that we know what we're doing here. I guess in something that's this kind of long, or I don't even know how long this is going to be, like I said, but I think it's important for us to talk a little bit about why these things are important. Net ionic equations, what they really do is they focus our attention. In one of our previous lectures, we talked about the solubility of ionic compounds. And when ionic compounds are soluble, they will split. Okay, so those ions, when they split in water, let me see if I can draw water here. Okay, so that's a beaker. Then what the ionic equations allows us to do, especially the net ionic equation, is just focus on the things that are changing. Just focus on the parts that are undergoing the chemical change, the chemical reaction. And so to get to that focus, though, it can be a little tricky. So that's what we're here to. This is one of the reasons why I record my lectures. That way you can hear me talk about it. You can go over it. You can pause it, rewind it, fast forward, whatever you need to do. You can see the examples a couple of times, whatever, right? But back to here. Here's what I'm going to do. Okay, we have a beaker full of water, and I am going to, in that beaker, throw sodium chloride. Okay, now sodium chloride, when it's not in water, will stay as one big unit. Opposites attract. This is a positive ion, this is a negative ion, and they're very strongly attracted to each other. Now what happens is when this goes into water, water will actually be able to interfere with the bonding. And so now what we have is a sodium ion and chloride ions floating around. And yes, they're attracted to each other because opposites attract, but they can also be attracted to other things. So by putting ionic compounds in water, we're able to kind of facilitate chemical reactions that otherwise may be difficult to have happen. I'm going to pick another element, let's see, or another ionic compound. Let's do lithium. Lithium fluoride. Okay. Now, again, lithium fluoride is one big thing. We talked about how ionic compounds need to maintain their balance and charge, balance each other out and things like that. So, but when this thing goes into water, you get Li and F, and now these two things are floating around and are able to act independently with each other, and that's only if those compounds are soluble. Okay, so it would probably benefit us to have a solubility chart. Oh, look what I have on the next slide, which you probably know because you've already looked at the slides. But this here tells us what is soluble and what is not soluble. What will split up in water and what will not split up. Okay, and that is super important because when they split up, a reaction is more likely to happen than when they don't split. Okay, so now, that's what I've said in the past minute really just emphasizes this point, is that when they're in water, the ions, because they're separated, they can react with each other more easily because opposites attract, and they typically will want to make something that is insoluble. to make this easier, what we're going to do is we're going to progress through what we call, not what we call, we're going to progress through a reaction in 3 steps. We're going to do a molecular equation, a total ionic equation, and a net ionic equation. Okay, the total ionic equation here is what the book calls the ionic equation, and then the net ionic is the net ionic. Okay, and then the molecular equation is what we start with. So what I'm going to do is I'm going to go to some of the examples in the book. Okay, so here's one of the examples in the book where we have 2 ionic compounds. Okay, let's make sure that we understand that this is a metal and a nonmetal. That's a metal and a polyatomic ion. Here's our first look at a polyatomic ion. And so, but when we see metals, we know they're ionic compounds. Okay, so these can react with each other, and we can facilitate that reaction by putting them in water. So what I'm going to do is I'm going to kind of ignore everything here. So watch what happens. I'm going to take a big beaker because I need a lot of space, and then I'm going to fill it with water. And now sodium bromide, NaBr. Well, we can go here. Look, bromides are all, they're all number 3 here. I can't write on this. Copy. Let's see. Boom, boom, boom. You can see my edit, paste, optimize. Okay. So you can see here bromides are soluble, except with silver, lead, copper, and mercury. Okay, so let's go back here. Okay, so this looks like a little happy face here. Okay, so this thing is soluble. Okay, so we're going to not have NaBr, but Na plus and Br minus. And how do I know the charges? Because back on the periodic table, sodium is here, it's in the 1 plus, Br is here, it's in the 1 minus. Okay, so I'm going to put those here. I'm going to put some Na, and then I'm going to put some Br. And then, to emphasize that these are not bonded, I'm going to put them in circles. Now, sodium nitrate. Okay, you're going to see that nitrates are all soluble. Okay, look, almost all nitrates are soluble. Okay, so we'll go back here. Here's sodium nitrate. I'm going to write this in green. So this is found as Ag plus and NO3 minus. Now you wouldn't have to know what the charge on silver was, nor would you have to know what the charge on NO3 minus is. I would give those to you. But here we go. So that means Ag plus is in the water, and then NO3 minus is in the water. Now all of those things are mixing up, and remember, opposites attract. So what's going to happen? And I'll show my opposites attracting with purple, my favorite color. Are silver and sodium going to attract each other? Not at all. Okay, those are the same charges. Okay, how about sodium? How about NO3 and Br? Are they going to attract? Not at all. Again, positive, negative charges. They're the same. What if these two came back together? What if these two attracted each other? Which they are. Well, because they're soluble, they're going to come back together, and then they're just going to split right apart again. Okay? The same is true with these. So what ends up happening is that now the Na has to be attracted to the NO3 minus. This is a plus charge and a minus charge. But then the silver is attracted, the Ag is attracted to the Br minus. And so what happens, I don't know if anybody remembers, there was a TV show called Wife Swap. Okay, and so it'd probably be better, more politically correct to call it spouse swap. But the point is that sodium used to be with Br, but now it's going to end up being with NO3. Silver used to be with NO3, but is now going to be with Br. And why does that reaction happen? Remember, those reactions happen because one of the compounds would not be soluble. So if we go back to our list of solubilities, my guess is, if you look here, silver and bromine, when they're together, are not soluble. So that means if they're not soluble, they stay together as a solid. So these two things find each other, and when they find each other, they hit, and then they leave because they come out as a solid. Okay, so let me get rid of this junk. Okay, and you scream along at home. Okay, so NaBr breaks apart. We already figured that out. So we're going to write that as Na plus Br minus. Now we're going to write a reaction. Okay, so we have sodium plus and bromine. Sorry, Br minus. Let me make sure that I get that right. You guys were probably screaming along if that's a minus. So it's these two things. It's not together. It's in a compound. So this is actually, if I'm going back to what I said back here, this is actually step 1, already written out for us. Okay, this is the molecular equation. That's step 1. Okay, so now what we're going to do is we're going to do step 2, where we split everything that is soluble based on the solubility rules from that chart. Okay, so now it's plus, and then silver and AgNO3 can break apart. Ag plus, then plus NO3 minus, and that reacts to form. Our arrow doesn't change. Okay, here's the end of the reactants. Here are the end of the reactants. Okay, and now this splits apart. Na plus. Let me get rid of that here. Make sure that it's written clearly. So it splits apart into Na plus NO3 minus. And I always run out of room whenever I write these, but notice this guy does not. That's the thing that comes together, and this stays together. Okay, so now we have here what we call our TIE, our total ionic equation. That's step 2 here on our list of things that we do. Okay, let's see, back to here. Okay, so now in step 3, when we're writing our net ionic equation, and this is where the chemistry, where we get to focus right in on the chemistry, is the chemistry happens when things change. So all we really have to do is compare, let's see, sodium, Na plus. Is it different on each side of the equation? Here it's Na plus, here it's Na plus. So it's not this. It is the same. It's not different. So we're going to cross it off. We're only going to keep those things that have changed somehow. Okay. So now let's see. Bromine. Look, this one, it's an ion. Here, it's part of a compound. Let's see. Ion, compound. It's different. So we're going to keep it. We're not going to touch it. Okay. And then silver. It's an ion. Here, it's part of a compound. So we're not going to touch it. The NO3 minus. Notice here, it's all by itself. It's all by itself. And so to go from the TIE to the NIE, the net ionic equation, we just cross off the things that have stayed the same. So now this is going to be, and I'll do it in black here, Br minus plus Ag plus reacts to form AgBr. Okay, and we've gotten rid of these guys. These guys actually didn't change at all. They're just hanging around watching the reaction happen. Okay, and so that gives them a special name. I'll talk about the special name in a minute. Okay, but so these guys, because they didn't change, they didn't undergo any sort of reaction, that just means that they were watching the reaction happen. They weren't part of the chemical reaction. So now this is what we call the net ionic equation. And in the list of steps, this is step 3. Okay, so let's keep moving. Here's the funny thing. And so I'm gonna take a little break from writing net ionic equations here. And I'm just going to show you this. This is a compound, MgF2, and this thing is soluble. And when it's soluble, it splits up into Mg2 plus. Now notice it splits into fluoride, and when we write this, fluoride is F minus. The formula of the ions do not change. That's determined by the periodic table. F is here. It's going to be 1 minus, and that's the way it's going to be. So here we have Mg2 plus and F1 minus. How many F's do we have? We have 2 F's. So this we're going to put here, and we're going to say that Mg2 plus 2 fluorine ions, okay? And so that's how we indicate that. Now the only thing that can happen is it can be a little tricky here when we split this apart. Okay, I draw the line there to split apart. How many potassium ions do we have? How many Ks? Right, we have 2. 2K plus, and now this is a polyatomic ion, and that polyatomic ion stays together. That 4 is part of the ion. Okay, so that could be a little tricky. Then that's 2 minus. Okay, so we can tell here we have 2K plus SO4 2 minus. We have 2 of those things. Okay, so let's try this. Here's an example from the book again. Okay, and you can see this one uses some numbers and some coefficients and some things like that. Okay, so this is already step 1 done for us. Okay, this is a molecular equation. That's the me already done. Now we need to go from the molecular equation to the total ionic equation. And then we look up what the solubility rules are. And you will find that, and I'm just going to write it above here, that this is soluble, and this is soluble. This is insoluble. I'm going to put a little I there for insoluble, a little lowercase I. And then this, if you remember from the other example, NaNO3, is soluble. Okay? Or maybe not from the other example. I don't remember. I feel like we did this at one point. So, here's the thing. We have 2 things that are soluble as a reactant, and then 1 thing that's soluble as a product. So, in order to go from step 1 to step 2, we're going to take the things that are soluble and split them apart. And we have to keep the charges on it. So that's going to be Mg2 plus, and now look, we have 2 nitrates, 2 NO3s. So I'm going to put a coefficient there, 2 NO3 minus. Plus, let's see, look, there's another one of these. There's 2 Na plus. And now this thing stays all together. It's a polyatomic ion. Plus CO3 2 minus. And that reacts to form MgCO3. Why didn't I split that up? Right, because it's insoluble. It doesn't. Insoluble things don't get split up. Plus, and now this 2 out in front means there's 2 of everything in this thing. So there's 2 Na plus 2 NO3 minus. Whew. That's a pain in the neck. It's hard. There's a lot going on here. Okay, but now we have our TIE. This is our TIE. Now from the TIE, that's kind of like our work to get to step 3, which is our net ionic equation. Okay, our net ionic equation, let's see, we're going to cancel out anything that stays the same. So let's see here. Here's Mg, here's Mg, here it's an ion, and here it's part of a compound. So that's different. That has undergone a chemical change. Okay, look at this. Here's 2NO3 minus. Here's 2NO3 minus. These guys are just watching the reaction happen. They're not participating in it. And the same is true here. 2Na plus, 2Na plus. So we're going to cross those guys off. And now look, CO3, 2 minus. Here's CO3, and those guys are still part of the same, have changed. Okay, so the magnesium and the carbonate, the CO3, have changed. The Na and the NO3 are just around watching. And you want to know what's really funny? The things that just watch are called spectator ions. Right? Spectators just sit in the stands and watch. Well, these two ions just sit in the beaker and watch the reaction happen. So now what we're going to do is we're going to do step 3 here, where we're going to write the net ionic equation. And the net ionic equation is going to be Mg2 plus, we skip the things that were crossed off, plus CO3 2 minus, and that's going to react to form MgCO3. And there you have it. Okay, so I would expect that we'll do some more work on this in class, where we can try to figure out how things are separated and whether we have spectator ions or not, writing that ionic equations. But there's 2 examples that you can work through, and you can try to stop, rewind, pause, fast forward, whatever it is that you need to do, and you can see if you can get it. Okay? Have a great day, and talk to you soon.